Hi, our project is the Wikipedia Hyperlink Network Analyzer, and our team members are Ritvik Gandasari, Sanjeev Iyer, Gagan Devermont, and Sarah Zimmerman. Our project was based around the game WikiRace, in which a player starts at one Wikipedia page and has a destination Wikipedia page that they must reach by only clicking the hyperlinks contained within each page. We wanted to find the best strategy to win this game for any two destination and start pages. To do this, we wanted to explore different algorithms that will let us find an optimal strategy. So one of the algorithms that we wanted to do would help us find which pages are most often used in our shortest paths. This will let us find a page that maybe we want to get to in order to reach our destination because it's used many times in the most optimal path. Another thing that we wanted to find is if components were strongly connected, meaning that one Wikipedia page would be connected or lead to another Wikipedia page because every node has some sort of link that will take you by either 1 or maybe 10 links to a different page. Our data was in a TSV file, and this data was accumulated through a Snap Wikipedia navigation path set that we got from Stanford. And it contains 4,000 articles and has all the links that those articles go to. In order to use our data and properly have our graph structured, we needed to parse our data first. So we were given our data with edges in a TSV file where the tabs were separating the start node and the edge and the end node for each edge. And using this, we created an adjacency list that mapped each node to whatever edges that it led to, and we had our adjacency list created based on that.
Hello, this is Ritvik, and for our traversal, we just do the BFS traversal on our graph, and the issue we encountered was that our whole graph is actually not one full connected graph. They're just connecting components, so there's multiple subgraphs. So if you start BFS at a certain node, it's only gonna go through the original traversal for that specific subgraph. So what we had to do was implement another method such that one of the methods takes care of just doing BFS straight up on any subgraph, and then another method to make sure that every subgraph in our whole big graph is accounted for, and we did that by keeping track of which nodes are visited. So once you do the traversal for a singular node and a singular subgraph, the first unvisited node, that's the one you do the next BFS traversal on, and then we just kept track of this by having different vectors for the traversal. So you would return a vector of vectors, each vector being a different traversal, a different BFS traversal for each subgraph.
The first algorithm we implemented for a project is Kosa-Raj's algorithm, which finds all the strongly connected components within a directed graph. A strongly connected component of a directed graph is when there's a path between all the vertices in a subgraph. As you can see in our little diagram below, the nodes 1, 2, and 3 are within a strongly connected component since they can all link back towards one another. And 0 and 4 are in their own component as they can't link to anybody else. And in terms of our data set, however, a strongly connected component represents all the different articles that can link back to one another. So in order to find these strongly connected components, we had to perform DFS on our graph and then reverse our graph, which is just like reversing an adjacency list, and then perform DFS again on this reverse graph to find any matching components that contain the same vertices which link in both directions to each other. The way we tested Kosa-Raj's algorithm is by using a small data set of just integers, which again can be represented by that small diagram below. And we found that the big O runtime of Kosa-Raj's was O of V plus E, where V is vertices and E is edges.
So the last thing that we looked at for our graph was betweenness centrality, and this is actually the most essential measure for the game of Wikispeedia, and it tells us the most about what strategy to take. Because Wikispeedia is all about going from your starting Wikipedia page to the ending Wikipedia page the fastest out of everyone who's playing. And so betweenness centrality measures how often a certain page is present in the shortest path, in any given shortest path from any node to any destination node. So it sounds like it would be a pretty easy feat, but it actually turned out to be a little bit difficult for us to figure out. So we knew that BFS gave us the shortest path from one node to every other node in the graph, a full traversal. And this was a really great starting place. But it was hard for us to figure out how to store the path from one node to a given ending node. Because at the end of the day, there's a lot of algorithms for finding out the total number of paths, but we wanted to store all those paths because the intermediate values were important to us, not the beginning and the end. So what we did is we took BFS as our starting code and we implemented a map into it that mapped each node, which I would call a destination node because that's where you want to end up from whatever starting node you pass through. And it mapped it to its path. And you could keep up with this because BFS implements a way that you have your current place and then you enqueue all the places that you can go from there. So every time that you enqueue, you would take the path of the current and you would make that the value of the one that you enqueued, and you would just add on the key value to it, and that would give you your path from your start to your end. And then you just do a little bit of basic counting. You count how many times a node is present in a path, and you keep track of that in a separate map, and then at the end of it, you just divide by the total number of shortest paths that we found. So this actually ended up working really well for us, but at the end, we figured out that we didn't actually take into account all the shortest paths, which was definitely a development that we would do if we had more time to. So BFS only gave us one shortest path from each node to each destination, which gave us enough information to get a pretty good ballpark estimate of what the between centrality was for any node. But it's obviously not a full measure for not taking into account the fact that there could be multiple shortest paths from one node to another. So that's one thing that we would really like to improve upon if we had more time. But at the end of the day, between the centrality told us a lot about what strategy would be the best to play Wikispeedia.
We found out a couple of strategies to get better at the game. So looking at the shortest paths and between centrality method, we realized that geographical locations such as Africa, England, or the United States actually have one of the higher values for between the centrality. So if you want to find the shortest path, trying to go to those pages, so Africa and whatnot, would be easier for you to get to the end result. And same goes for countries and other places and other time periods like 19th century, 20th century, and whatnot.
We used Kosa-Rogers' algorithm to help us find all the strongly connected components within our graph. When we ran our algorithm against our dataset, we found that there was one component that was almost 4,000 nodes, while the other only had a couple of nodes in them. The component that had almost 4,000 nodes, it had thousands of topics and different articles that all related to each other, and that just shows how deeply connected it is, and that it's possible to reach a majority of nodes from any given node within that component. However, even though it doesn't really provide us a real strategy we can use to help us win the game, it's possible to see a path between any two articles, even if they're pretty unrelated to just like normally looking at them.
The biggest things that we enjoyed about this project was that the code was actually super meaningful because the results we got were actually applicable to something outside the code. So the results we got from arbitrary centrality and the other methods was actually help us get better at the game. Wikispeedia give us better strategies and kind of give us what nodes to look for in the game. And the data was actually super easy to read and understand as we parse through it and work with it, because there are actual Wikipedia pages that you can understand, okay, so this page is connected to that, and then that's connected to this. And then the biggest issue we had was that the original data set is only it's very limited, and it's not actually the full Wikipedia network. So it's the whole project that we did is only on a smaller subset of the whole data, of the whole Wikipedia data. So if in the future if there's access to the whole Wikipedia data set, we'd be able to run our code on it, and that would help us get even better at the game Wikispeedia, because it's it encompasses a bigger part of the whole network.